Okay. Hello, everyone, and welcome to the second session of the day. I have the pleasure of introducing Sebastian Jaimungal, who is professor at the University of Toronto. Sebastian is famous for his works, in particular on algorithmic trading, and more recently on mean field games and their applications to financial markets. So please go ahead, Sebastian.
Great. Thank you, Peter, for the introduction. And good afternoon, good morning, good evening to everyone around the planet. It's a pleasure to take part in research in options. I can't actually remember what my count is now, but it's pretty high up there. So I've not been to every one, but it's every single one I've been to has been a real pleasure, both research-wise and of course all of the friends and research that we've had to listen to through the years. I know that this particular session or this particular conference is dedicated to Marco, and I wanted to say a small thing about that. In fact, a large part of what Peter mentioned there, my sort of trajectory, if we will, my excursion, if you listen to Rama's talk, off into algorithmic trading land began, in fact, with one of Marco's first papers in the area on market making, together with Sasha Stoikov. And that really sent me down this long path, which was quite fruitful. And even yesterday, Marco was talking about liquidity and liquidity risk, and there are flavors of that in Peter's talk this morning when he's referring to looking at electricity markets and intraday electricity markets and how agents interact with liquidity risk, playing a role in how they form equilibria. Another piece of work that's somewhat tied in is JP's work yesterday on MFGs and MFCs, and we'll see how that plays in here. So today, I'm speaking on mean field games and equilibrium pricing in renewable energy certificate markets. It's work that's being done jointly with my current PhD student, Arvind Srivastava, and a postdoc of mine, Dina Ferozi, who's now at University of Montreal. And I'll go through, in fact, I'd rather just get all of these points listed here. So the idea behind REC markets, these renewable energy certificate markets, it's a way to incentivize clean energy. And the basic idea is that a regulator imposes a floor on the minimum amount of RECs that a firm has to produce. And if they don't meet that minimum amount of RECs, then they're penalized by every REC that they fall short. And firms can trade these RECs between one another, and that's how their prices are determined, just by this buying and selling from demand that's in the market. What we are trying to do in this piece of work is come up with a way of developing an equilibrium pricing framework for RECs, because there's been some studies on them, but not been a ton of work, and they're related somewhat to cap and trade, and we'll see exactly how that relationship works here. So what we'd like to do is look at a collection of firms that are regulated by these REC markets, and is there a strategy across all regulated firms such that we achieve a Nash equilibria and an endogenous price. So that's the key point. We want to account in this context for the cost of generating electricity, because generating electricity is not free. You might have some infrastructure that you've already built, but if you're to speed up your generation, you might have to build new capacity. As well, when you're trading RECs, as opposed to previous works, which just assume that you can instantaneously trade from one position into another at the price that is currently displayed in the market. Well, this is not the case, as Marco very well explained yesterday, that there's this liquidity risk in there, and we'll account for this trading cost or liquidity risk, if you will. And we also want to account for the fact that there are other agents that are trading in the market, and their actions affect the price of SRECs. They also affect, therefore, they affect the way that you will behave. One thing that I'm not going to discuss in this particular piece is at least in the development of the theory, is the fact that there are agents or firms, really, of different types. So not all firms are the same type with the same type of risk preferences and the same type of penalties and so on. Instead, there really should be subpopulations of firms, like a third of them are of this type, and another quarter of this type, and then the remainder of type C. So this generalization is covered in the paper, and I will show some example, but I'll develop the methodology as if we had homogeneous agents. So this is a non-existent list of the literature that's in this area. So first of all, there's just the cap and trade literature, which is somewhat related, but I'm not going to talk too much about it because it's not directly related to what we're doing, but tangentially. However, in the rec literature, there's a price modeling that's been done by Michael Kulan and his co-authors, and there's a couple of other more recent papers. I didn't actually put them on here. We have a single agent piece of work together with Arvind earlier on, but more recently there's been a lot of interest in MFGs in price formation. There's a paper by Diego Gomez and Fuji and Takahashi on price formation in equilibrium with using MFG technology. As well, we saw that Peter's talk, in fact, he only presented a piece of the work that he has on this, and there's a portion of it which actually looks at the MFG formulation there. Fracking was also a piece, a related work by Ronnie that looks at MFGs in the context of energy markets. And again, Peter has a problem on entry-exit problems where using MFG technology in the context of this energy markets as well with Renee and Dumitrisco. So let's go on to our actual setup of the problem. What we're interested in is we're looking at formulating the optimal behavior as a stochastic game, of course. So I need some notation in order for you to get into the details of the problem formulation. So agents have controls, alpha, which represent there's going to be two-dimensional controls here: generation rate and trading rate. So they generate electricity and then they trade RECs. There's state variables which correspond in this context to the number of RECs that they hold. And then there's a performance criterion that they're seeking to minimize. So they're trying to minimize total costs. There are multiple firms involved, so we need to account for the distribution of other firms' states, and we'll call this mu square bracket n. In addition, because we're looking at buying and selling RECs, we need to know what price those are traded at. And as I mentioned at the start, these prices are going to be determined in equilibrium. I'll mention that we're going to look at just the not the single agent case, but the case with homogeneous agents. There's a couple of further notation. So let's go back here again. So alpha is controls, which represents generation and trading. X is the state variable, which generates the number of SRECs. S is price. But the regulator is imposing something on us, and the regulator imposes a penalty per unit of non-compliance P, and R represents the floor level, the requirement that the regulator imposes on firms. And then there's a generation cost parameter and a trading cost parameter. So we'll see exactly how those play into the performance criterion here. And this is the details of the performance criterion and the state dynamics. So over here, you can see that the controls are broken into two pieces, as I mentioned: the rate at which you generate electricity, the rate at which you trade SREC, the amount of RECs that you hold at a particular point in time, the empirical distribution, and then here's how the state variables evolve. So the amount of RECs that you have at any one point in time come from what you've generated through generating clean energy and what you've bought from the REC market. However, because when you plan to generate a certain amount of electricity, you don't actually get it, and particularly if you're thinking of it coming from solar means, instead there's some noise around that, and that's where this diffusive term comes into here. So while you are able to target a certain generation rate, you are going to have noise around it. When you buy and sell RECs from the market, this gamma component, this is fully deterministic, or not, I shouldn't say deterministic. If you aim to trade gamma, you will get gamma. So we're assuming that for every buyer, there's a seller. In terms of the costs associated with this firm, there are three components. There's the generation cost, which looks at deviations of your generation rate from some baseline. And zeta here represents the strength of that cost. And then whenever you buy or sell, there's some sort of transaction cost, or if you like to think of it as liquidity cost as well, it's effectively the same. And this is a way of proxying this notion of trading too fast in the market is going to be too costly. So you have this extra transaction cost. And then when you purchase shares, then there's also a cost associated with buying those shares. You're trading at this particular rate, but this is the price that you receive. So this is going to be a total trading loss, if you will. If you're selling and gamma is negative, then that becomes a profit. And we'll see that there are situations where it may be buying or selling. Finally, there's a terminal penalty. This terminal penalty, so this running cost, if you will, here goes into the agent's performance criterion, and we integrate it from 0 to capital T. And in addition, there's a terminal cost associated with the regulatory penalty on the agent. And this regulatory penalty forces the agent to pay the maximum of R minus X and 0 times P. So for every rec that you fall short of R, you're penalized an amount P. And we've regularized this in order for us to, in order for the theory to work, in fact. So you can think of delta here as as a regularization of the hockey stick diagram, of the hockey stick payoff for the put that the regulator imposes on you. The next bit of information that we need to know is how are the agents adapting their strategies? To what information are they allowed to use? Well, they're allowed to use the information about the entire history of their rec. They're allowed to use the information about the entire history of rec prices. They do not, however, have access to what other agents are doing. And this limited information, this sort of restriction of the information set of an individual agent to what's personal to them, makes the problem quite challenging even for the finite player game. And that's why you'll see we go off into the infinite player game here. So this is a partial information type setup. And the set of strategies that we're going to impose are the usual type of restrictions that we'd want. We want square rootability, we want the generation rate to be positive, and we want the generation rate and your trading rate to be adapted to this filtration that is your personal filtration. And what is it that we seek? Well, the usual thing. We seek a Nash Equilibrium, which means that we're looking for the strategy for which all agents, or which any particular agent, if they deviate from it, then they will suffer. In addition, we're imposing the clearing condition that for every buyer, there's a seller. So we must have that the sum over all over all rates sum to 0. And as I said, because of dimensionality, it's actually not so much dimensionality per se, but really information restriction that makes it much more challenging. So the way that we're going to solve that issue and resolve that problem is by taking n going to infinity. And here, when you do take this limit, as you saw in JP's talk yesterday, the individual agent becomes negligible. And instead, you have individual agent playing against a distribution of states from all other agents. And the goal in mean field games is to obtain that distribution of states of other agents that's self-consistent with the system. And we'll see exactly what we mean by self-consistency. So when we go to the mean field limit, we remove the square bracket n so that it's not a finite number of players, but rather an infinite number of players that are involved here to generate this distribution. And we use a notation as well for the SREC price to be given by just superscript mu without the n there to define the finite population. So what is the infinite population dynamics? Well, this looks very, very similar to what you've seen before, to the previous one. The only difference is that here we now have the mean field distribution that shows up. And this is the terminal value of that mean field distribution. Once again, we seek a Nash Equilibrium. And what does equilibrium involve now? It involves not just seeking for the arg-inf over some empirical distribution here, but rather over the mean field. And we need to find a mean field that is consistent with the law of the states. So this is how everything is tied together in a fixed point way. In addition, of course, additionally, we need the price that leads to market clearing. So we need to ensure that the sum of gammas are 0. This is the general setup of the way that we've solved the problem. I'm not going to go into the details of the mathematical, of the proofs of the various pieces of this work, but here's the big picture idea. What we do is you say, let's suppose that we have some distribution of agents, of states. We use a variational analysis approach to obtain what is the Nash equilibria for all of the agents. And this equilibria depends explicitly on this distribution of states and an adjoint process y. Once you impose, so this, remember, this alpha tells the agents how do we trade and how do they generate electricity. Once they obtain that in terms of these two things, which at this point are not known, we impose the clearing condition, which then forces us to find the SREC price. And this SREC price is now, again, in terms of this same adjoint process and these and the mean field distribution, or the tentative distribution. This collection of SREC prices, together with this variational analysis approach, results in a forward-backward stochastic differential equation for the states of agents and their adjoint process. You can then solve this FBSDE in principle. Doesn't mean that it's solved explicitly, but in principle it's solvable, and we prove uniqueness and existence of the solution of the FBSDE here. And from that, you obtain a law of the states. And in order for this to be a solution of the mean field game, we need to ensure consistency of our input, mu here, and this law. So very much, if you saw Jean-Pierre's talk yesterday, he had a very similar general steps. These particulars about clearing conditions and the variational analysis is not there because he took a different approach for solving mean field games, but we take this variational approach. So what are the key results? We have that the mean field flow. If you're given a mean field flow, then the optimal rate of generation is given by the base generation plus the ratio of your penalty per unit of missing rec to the penalty associated with generating, multiplied by the adjoint. And then the adjoint process itself is, and then the generation trading optimal trading rate is given by 1 over the cost associated with trading of the scaled penalty times the adjoint, and then you subtract the SREC price here. And the equilibrium SREC price turns out to be the penalty times the expectation of the adjoint under this given measure mean field flow. And the terminal condition for this adjoint process has this form. So what exactly is this F delta prime? Well, it turns out it's very close to the indicator function. So it's effectively a non-compliance probability. And the deviation from the indicator is only due to the delta regularization. So if you look at the result that we had on the other slide there, you can think of the SREC price as coming from, as being written in this form. It's P times the integral over the probability that an agent underperforms, where we take the averaging over the distribution of agents. And this contrasts with previous work in this area, where others find that the SREC price should be the probability of the sum of total SRECs being less than the total requirement. The reason why this result comes out in these previous works is that they've ignored trading frictions, this cost of liquidity, the cost of being able to change your position from one level of SREC to another was assumed to be 0. You can instantaneously do it. However, of course, in real markets, that's not the case. And when you account for that, you obtain instead an averaging of the probabilities rather than a probability of the average. If you insert those results, this is the particular FBSDE, and let's not investigate it too much. It's just it looks as if it's a really nice MVS FBSDE, but the fact that the terminal condition isn't quadratic or linear makes this thing be very difficult to solve analytically. However, even if we can't solve it analytically, we can come up with some numerical situations. But even before that, we need to ensure that there exists a solution, and the solution is in fact unique to the fixed point problem. Because remember, here we say, given a mean field measure flow, this is the FBSDE for the state and adjoint. But what we actually need is we need mu to be endogenously defined. And we were able to prove, in fact, that there does exist a mean field distribution and a progressively measurable triple that satisfy the MV-FBSDE such that this particular measure flow coincides with the law of the states. And moreover, there is only one solution to it. So there's in the last couple of minutes that I have here, I'm going to show you some numerical results by where we developed a numerical scheme for solving this problem. So the numerical scheme is we initialize the mean field distribution using some naive assumptions such as the firms generate at the baseline trading rate and they don't do any trading. Then you can obtain a distribution of the states. And from that base mean field distribution or measure flow, if you want to call it that here, you then use as an input, you solve the FBSDE, and there's some nice techniques that we developed for solving that FBSDE, which depends on the flow of measures as well. Once we solve that FBSDE, you end up with now a distribution of states, which is an updated distribution for mu, and then that goes back in to solve the FBSDE again, and you keep repeating until you converge. And once you've converged, then you output the controls, the mean field distribution, and the price dynamics. So, so this would be this is a way of solving it numerically, but let's remind ourselves that, in fact, our original problem is not the mean field problem. Our original problem is, in fact, the finite player problem. And what we need to do is we need to ensure that our solution forms a viable solution for the finite player problem. And one additional little corollary that's part of the proof of this analysis is that the adjoint process turns out to be Markov in the state variables. And if we use that adjoint, that Markov process for the adjoint and apply instead the finite player dynamics here, then we can show that this actually leads to a epsilon Nash equilibrium. As well, there's an equilibrium price where we simply replace the Markov function and evaluate it not at the mean field of states, but rather the finite population. So this is just definitions of epsilon Nash, and what we are able to show, in fact, that set of controls that I just showed you do indeed form an epsilon Nash equilibria, which means that the finite players can improve by deviating from this strategy, but they can only improve by an amount epsilon, and that epsilon goes to 0 as the number of players goes to infinity. And here's a simple simulation. So we looked at two subpopulation types, and in fact, it's just nicer to go to the graph. So there's subpopulation 1, subpopulation 2. On the horizontal axis is the rec inventory that they start with. The blue histogram here is the initial inventory of the first of the set of agents that are in subpopulation 1. The blue here is the initial distribution of the rec inventory for those that are in subpopulation 2. And what you see here in the different shades are the evolution of the empirical distribution when agents follow excuse me, when agents follow the finite population mean field solution. And this is the distribution that they converge to. The solid lines that you see there correspond to the mean field distribution that you would find in the mean field limit. So this is showing you that the finite population histograms that you've got, that we show the evolution of, are quite close to the mean field solutions. And this is the aggregate associated with the mean field distribution for all agents. And you can see that it starts off, it might be a bit challenging to see here, but the initial distribution starts off being bivariate. There's a double hump because there are two population types. And then as time evolves, it becomes unimodal. And that's because all of the agents are trying to meet this rec requirement, but not all of them are. Some of them are exceeding the rec requirement, some of them are falling short. And I think what I'll do in my last minute is just highlight the main contributions here. So what we've done is we solve for the optimal behavior for firms in rec markets together with the equilibrium price. We've shown how the solution leads to an epsilon Nash and prove uniqueness and existence, and while incorporating the impact of other traders, trading frictions, and generation costs. There's some of the current work that we're doing is extending this setup to the principal agent formulation, because here we assume that the regulator gives a particular penalty, which is the real penalty that is imposed in the real world. But you could ask the question, what should the penalty be in order for the principal, which is the regulator, to attain a certain goal? And we're about to post something on this work, hopefully fairly soon. And the setup is amenable to looking at generalized equilibrium pricing with FFGs, and we're working on this as well. So with that, I'll say thanks a lot for your attention, and you can find the paper on arXiv if you're interested in this line of work. I'm happy to take questions.
Thank you very much, Sebastian, for this very nice talk. Please go ahead. I don't see any questions now in the YouTube chat, but please go ahead and type your questions. In the meanwhile, maybe I can ask a small question regarding this principal agent setting.
Mm-hmm.
I have the feeling that sometimes the principal agent setting is actually simpler, because for a mean field game, you have to solve a game problem, whereas for the principal agent, it's an optimization problem. So do you agree with this?
Well, okay. We're thinking of it as a principal with multiple agents. I shouldn't say a principal and a single agent. It's really a multiple. So we're imagining that the regulator imposes some penalty on all firms, and once that penalty is defined, then all firms have to form an equilibrium, right? Mm-hmm. And they act optimally. Then this feeds back into what the principal would value their actions at. And then the principal needs to optimize over this terminal penalty. And there's this wonderful work by Sanikov and Nizar and so on that have a nice way of looking at this by rewriting it in terms of a control problem where they control the adjoint of the principal, right? So we're going along this line of work. There is some work already in that general direction, but we're taking a different perspective of it. That's by Dylan Posami and Eli, I believe. Yeah.
Okay, thank you. Okay, I still don't see any questions. Maybe they're all waiting for the break. Still have 2 minutes.
Not a problem. I ended too early then. I could have stretched it out.
So do you have common noise in your game?
No, there's no common noise in this particular setup, but I don't believe that common noise is going to be a huge challenge for us here, because of the way that so you can see that the agents have idiosyncratic, because the noise in this context, let's go back to the original setup. The noise in this context is thought of as you would like to generate at a particular rate to G, but you can't account for what would actually happen. For example, if you have solar panels and you're generating solar energy, then you don't know what the sun is going to do, right? You can have all of your panels open up, but you don't know you can't control the cloud coverage. So there's this uncertainty there. And indeed, you can think that if I have a bunch of firms that are within the same region, then perhaps the cloud coverage in one in firm A and firm B, if they're in the same region, they should have the same noise component, right? So we could think of generalizations like that. We haven't done it, but we've thought through that. It seems as if the methodology should go through.
Okay, well, thank you very much. I guess now it's time to move to the next talk.